Hello everyone, and welcome to our presentation, a pipeline for distributed high-resolution 3D reconstruction of urban scenes from point clouds. My name is Feng. My co-authors are Amin, Sarafraz, and Christopher Mader. We're from the University of Miami. The presentation slides are available through this link. Today I'll go over the problem that we're addressing in the introduction, and I'll discuss prior work done to address this problem in surface reconstruction, and I'll describe our approach, our implementation, and our results. With the progress in aerial 3D acquisition technologies such as camera drones and aerial LiDAR, it's now possible to have 3D scans of large urban scenes. The result of such scans is registered and aligned to the same coordinate system, and then further processed and reconstructed to 3D mesh models. Large-scale mesh models have numerous applications, such as mapping, smart cities, and remote sensing. However, processing and reconstructing gigabytes of large-scale point cloud data with complex real-world geometry is a challenging task. It requires significant computing powers and memory usage that typical personal computers cannot afford. Aside from memory challenges, processing and reconstructing large point clouds requires significant amount of computing time, which may not be ideal for rapid reconstruction of large urban scenes. The following is a visualization of the whole process. This is an example drone flight. We use UAVs to collect videos from which video frames are parsed and used for point cloud generation through structure from motion. This is an example point cloud. It is then reconstructed to a mesh. The mesh is then textured or colored. The problem we're trying to address is how to reconstruct meshes from point clouds at scale, potentially reconstructing at city scale while addressing the problem of memory usage and compute time. While point clouds are unstructured and unorganized 3D point sets, meshes are triangles or polygons created by connecting points with edges. As a result, the meshing process typically requires the most memory overhead and compute time in 3D reconstruction. There are existing parallel methods that aim to either reduce the memory limitations or compute time of meshing point clouds. Using multiple threads on a single node can save time, but it is bound by the memory capacity of the node. Therefore, it can accelerate reconstruction, but it may be bottlenecked by memory usage when it comes to meshing large-scale point clouds. There are out-of-core methods that swap data between disk and memory. It can store more data into disk and swap into memory when needed. However, the compute time is bottlenecked by computer's I/O speed. Although these parallel methods would improve the ability to speed up computation or handle data larger than memory, they cannot address both memory and time challenges at the same time, and therefore would not address the challenges of processing and reconstructing large-scale point clouds. Besides distributed computing, the other component of this problem is surface reconstruction. Surface reconstruction is in the business of how do you reconstruct a surface from point sets that best describes the actual physical surface. There are two major approaches. One is the explicit geometric approach. One of the heuristics in explicit surface reconstruction algorithms is the ball pivoting algorithm. The basic idea of ball pivoting is that starting with a seed triangle, a ball of a given radius pivots around each edge of the current triangle and forms a new triangle when it hits another point until all reachable edges and points have been tried. However, the problem then becomes how do you select the best radius for the ball? When the radius is too small, the ball will slip through points, leaving holes in the mesh. It's best used when the point clouds are uniformly sampled with uniform distance between points. Other explicit geometric reconstruction algorithms include Delaunay-based triangulation. They're provably correct, but they require densely sampled, noise-free point clouds. It's difficult to meet these requirements when collecting data from the real world. Additionally, point clouds collected through photogrammetry are noisy and do not represent true surfaces of the real world. Triangulating these points directly will result in unnecessarily bumpy surfaces. A more suitable approach to mesh real-world point clouds collected using UAVs and photogrammetry is to approximate surfaces by first fitting an implicit function to the surface and then extract the isosurface using isocontouring algorithms like marching cubes. One notable reconstruction method is Poisson reconstruction. It uses oriented points, that is, points with normals, to compute an indicator gradient that is 0 almost everywhere and 1 at the surface, since indicator gradient is equal to inward surface normal. Then it fits an implicit function to the indicator gradient, which can be cast as a Poisson problem. The implementation of Poisson uses an adapted octree to represent the implicit function and to solve the Poisson problem. By increasing octree depth, we can get a higher resolution reconstruction which captures finer detail. Increasing octree depth increases mesh resolution in terms of triangles and file size, compute time, and memory usage by a factor of 4. Lastly, the mesh can be extracted from the implicit function using marching cubes. This is a visual comparison of reconstruction results using ball pivoting algorithm and Poisson. On the left is ball pivoting algorithm, and on the right is Poisson reconstruction. As you can see, ball pivoting algorithm is prone to leave holes in the mesh when point distance is not uniform. This visualization can be found on my website. To address the memory challenge of processing and reconstructing large-scale point clouds, we propose a fully independent, distributed multi-node method. In our reconstruction pipeline, we first chunk large-scale point cloud into smaller, manageable chunks. For each chunk, we add an overlapping boundary and estimate normals. We then use Poisson reconstruction to reconstruct the mesh. Afterwards, we merge meshes by cropping each chunk back to its original bounding box. The first part of the pipeline is to chunk point clouds. We assume that in determining the bounding boxes to chunk a large-scale point cloud, the z-axis can be ignored because its range is relatively small in large-scale urban scene scans. The task of chunking point clouds is essentially computing an x by y grid of bounding boxes. First, we will compute the axis-aligned bounding box of the entire point cloud, which is defined by the maximum and minimum points. Then, based on how much user would like to divide x and y by, we compute the x by y grid. Then we will crop the point cloud by x and y bounding boxes and output the chunks. While chunking point clouds can facilitate divide and conquering mesh reconstruction, it inherently cuts open closed shapes and may divide otherwise closed objects, such as buildings. Implicit surface reconstruction algorithms tend to assume that the inferred surface is a closed solid, and therefore their performance can be degraded when the shape is not closed. It will lead to degraded reconstruction along the edges of each chunk. To compensate this issue, we propose a solution to add an overlapping boundary to each chunked point cloud to account for the degraded mesh quality. In practice, a 5% overlap would suffice. Here we're illustrating how we are adding the overlapping boundaries. Essentially, we're scaling each chunk's bounding box by 5% and adding overlap points from neighboring chunks. By chunking point clouds into manageable chunks, we can distribute the subsequent processing and meshing of each chunk as an independent process on different nodes on an HPC cluster. Since chunking fully separates data, these processes are fully independent, and the failure of one process does not have an impact on other processes, and they do not need to share memory usage on a node. Although memory usage is bound by the capacity of a node, the chunking and distributed processing on multiple nodes reduce memory needed for each node. Next is normal estimation. Assuming that the point cloud does not have normals, we will estimate the normals by first doing a nearest neighbor search. Then we will use principal component analysis, or PCA, to compute its vertex normals. PCA finds the orthogonal basis that best represents a given neighborhood of points. It finds the best fitting plane by minimizing the average square distance from a neighborhood point to the plane. The normal is the unit vector orthogonal to the plane. Point clouds with normals can then be meshed using Poisson reconstruction with a user-defined octree depth value. Lastly, we will need to crop the overlap meshes back using original point cloud bounding box information. In the same way that we can reduce memory usage by chunking point clouds, we can also offset the increased memory usage due to increase in resolution or octree depth value by further reducing the chunk size. For Poisson reconstruction, increasing octree depth value increases time, memory usage, and number of triangles by roughly a factor of 4, as shown in this table. This is a visual comparison of Poisson meshes at various octree depth values. As octree depth value increases, the mesh resolution increases, which captures finer detail. We implemented our method on an IBM Power 9 HPC cluster with PPC LE64 architecture. After chunking point clouds, for each chunk, we write shell commands that handle each individual process. These shell commands are then concatenated to a shell script, which is submitted as a job to LSF job scheduler on cluster. To evaluate our method, we conducted experiments comparing time and memory usage for single-node processing and multi-node processing using our methods. Our experiment data is a point cloud at the University of Miami campus with 1.18 billion points. For single node processing, we processed and reconstructed the entire point cloud without chunking. For multi-node processing, we chunked the point cloud into 36 chunks and tested using both 15 nodes and 30 nodes. We significantly reduced the maximum memory overhead for each node with our 30 nodes experiment. We also significantly reduced the total time required for reconstruction by over one-half. The total memory required for processing the 1.1 billion points is roughly 250 gigabytes, which is over the memory capacity in most HPC systems. By chunking point clouds into smaller chunks, we managed to use only a little over 8 gigabytes of memory per node in our 30 nodes experiment, and the resulting mesh is high in resolution with no negative effects along the edges of each chunk. We have shown that large-scale 3D reconstruction can be handled using a distributed method on computers with memory capacity similar to personal computers, by first chunking the point cloud and then processing the chunks on each node. We have demonstrated that large memory is not required to process and mesh large-scale point clouds. By addressing the memory issue using our method, we can greatly improve the reconstruction resolution using higher octave depth values. The resulting mesh is high in resolution and shows no negative effects due to open shapes caused by our chunking process. We would like to thank the University of Miami Institute for Data Science and Computing Advanced Computing Group for allowing us to use their HPC clusters. These are the references. As mentioned in the introduction, large-scale reconstruction of urban scenes have applications in 3D mapping and AR/VR. This is an application of research. It's being applied to this Magic Leap development project called Tiling the Magic Verse, which aims to build a tiled 3D map of the university's campus. Tiles and meshes are being created using our pipeline at various resolutions for level of detail rendering. Thank you for coming to our presentation. Slides are available through this link.